Yes, my dear participants, today I am going to talk about, I have already covered MLR. Now, there is an exercise based on the above concepts, and that exercise says that create a data frame consisting of weights in kgs, height in centimeter, and age in years of all the students of BSc 5th semester. Fit a model, weight is equal to beta naught plus beta 1 into height plus beta 2 into age plus years, and write down your commands and conclusions about the analysis. So this was all about the exercise. Now I am going to talk about scatter plot matrix. You know, scatter plot, scatter diagram, actually it is like this thing. Scatter diagram, if we have x-axis on here, y-axis on here, and here pair of points, so this is known as scatter diagram. But if you have more than two variables, then we talk of scatter plot matrix, and that we will discuss using the function pairs in base R. So scatter plot is an extension of scatter diagram for more than two continuous variables. For making this scatter plot matrix, we have the function pairs in R, in base R actually. We shall make use of trees data for the purpose of illustration. So trees data you are already familiar with, so that's why I am using the trees data. Pair trees, panel is equal to panel dot smooth. So here these are the panels, like in trees data. See here, this is the girth and this is the height. So this scatter plot between girth and height is this one. Similarly, between girth and volume it is this one. Between height and volume it is this one. And since it is a scatter plot matrix, so it is a kind of symmetric matrix. So that's why this one A12 is nothing but A21. Similarly, A13 is nothing but A31. So similarly, you can have the graph like this. So this is the, here you are getting that these lines are not smooth line, they are not the straight lines, because they are computed on the basis of panel dot smooth, and that is a non-parametric function to using Loess to compute these. See, from above plot it is evident that there is a strong linear relationship among the variables of data trees using the see. Why it is linear trend? Because as you know, girth and volume, see here the points are around the line. Girth and volume, there is a strong linear relationship because points are around the line. So if points are closer to the line, that shows a strong linear relationship, and if points are away from the line, like between girth and height, points are away from the line, so there is comparatively weak linear relationship as compared to girth versus volume. Similarly, between height and volume, there is linear relationship, but not as strong between girth and volume. So this is the interpretation of this scatter plot. With we got this with the argument panel is equal to panel dot smooth. Actually here the argument is panel trees data trees, and panel is equal to panel dot smooth. So panel dot smooth is nothing but it is based on Loess, and it computes non-parametric estimates of these lines. Here we want a linear relationship among pairs. For this purpose, we need a function which will be fitted, which will be plotted, which will plot fitted regression line in each panel. So in each panel, see in these panels, we want linear regression line. So for that, what we have to do? We have to define a function pan1, naming pan1, which will implement these ideas. Pan1 is equal to function x comma y. Pan1 is the function of x comma y. So these are the arguments, and then this curly bracket from here to here, it is parts of the, it is the body of the function, and then points x comma y plotting character is equal to 18. So here we want to add the points with plotting character 18, and then m is equal to lm to fit simple linear regression model y versus x, and then ab line, we are adding a line which will take the points from here, regression coefficients m, lwd is equal to 2, and then we will dump this function, dump is equal to c. Then we can use the source.txt, and then we are using pairs, trees, panel is equal to pan1. So we are calling this function panel is equal to pan1. Now see what happens. See, this is the effect. Now we are having simple linear regression fitted in each panel. So this is the advantage of writing the function pan1. Now I will go into the basic commands, and here see here are pan1, before that here are panel, scatter plot matrix pairs. So here in this chunk we have written the command, this is the chunk of R, pairs, this is the labeling, pairs 1 of this chunk, message is equal to false, there should not be printed any message, warning is equal to false, there should not be any warnings printed. Then fig.cap, caption of the figure, scatter plot matrix for trees data, and pairs trees panel is equal to panel dot smooth. So when we run this chunk, we get this output. Now to fit here the simple linear regression line, we need to define a function, and the function is here. See, we are writing a chunk pan1, and here we have written the chunk name pairs1. Here we have written the chunk name, chunk label pan1, and then message is equal to false, warning is equal to false, fig.cap is equal to scatter plot with fitted lines. Define a function pan1 which will implement these ideas. Pan1 is equal to, this is the pan1 is equal to function x comma y, these are the arguments, and then points, to add a points x y, plotting character is equal to 18, and then m is equal to fitted linear regression line in each panel, and ab line means add a line, and here the regression coefficient, because m has the information about, actually I would like to explain these things. Say for example, if you have x is equal to say 2 comma 4, 2 comma 4 comma 7 comma 8. So this is x, and then y is equal to c, say for example 3, 5, 9, 12. So these are the y variable, these are the responses. When we fit M1 is equal to LM, it is y tilde x, and this fits simple, this fits the model y is equal to oh, this pen is not working. Okay, this fits actually this fits the model y is equal to beta naught plus beta 1 into x plus error. So this fit this model y is equal to beta naught plus beta 1 into x plus error. This fit this model. So here y stands for y and x stands for. So how we write the formula? In LM it is y tilde modeled as the function of x, and actually to get the scatter plot we can have scatter plot y tilde x, or this is equivalent to this is caps, its caps lock is on. Yes, now we have got scatter plot matrix. This is y versus, this is the scatter plot. This function plot y versus x, it gives plot, and we want to add a fitted line here. So see what will be the command. Here the command is actually ab line, and our fitted object is M1. So it will add a line, it has added a line, So actually for plotting this line only intercept and slope are required, and if you print M1 object, it has beta naught minus 0.307 and beta 1 1.439. So either you say ab line M1 because M1 has the information about beta naught and beta 1, and that then it plots the line. But we can plot this ab line. See, ab line means it is a plus b. Ab line means it is a plus b. It is a plus b. So here we can have ab line a is minus 0.3077 and b is I am not going to write b, rather just I am writing 1.4396, and Curl is equal to red. Curl is equal to red. So just to distinguish it. Now if we add this line, earlier line was black and we have added a red line. So it is on the black line exactly. So that means either you use ebb line M1 and that is equivalent to ebb line A is equal to minus 0.3077, this is intercept, and the slope of the line B, and color is equal to red. So, and here plotting character is, suppose plot x comma y and PCH is equal to, plotting character is equal to 18. So here it gives this kind of plot. It is a very good plot. It is very good character. But suppose you change this plotting character. Suppose you change this plotting character 15. See what happens. It changes this character. It is this kind of character. So that's why I have chosen plotting character is equal to 18 and then M is equal to LM YX and then ebb line M LWD is equal to 2, so that we can keep the thicker line. And then we are dumping this. We are dumping this. We are saving. We are dumping this to a file pan1.txt and then source pan1.txt to source it, and then pairs, trees. Now panel is equal to pan1. This function is being implemented, and suppose we run see, this is the result. This is the result, and we are getting these things. Suppose we want some changes, like suppose we want curl is equal to red. Then what it will do? It will add the red line, not the black line. See here, you can make changes. And here dumping means we are saving this to a file pan1.txt, then you can call this. Dumping and source are very useful because once you have dumped this, it will be available there pan1. See, this is the text file pan1. This is the text file which is saved in the same folder. This is saved in the same folder pan1, and you can make editing also. And source, to source it. So to dump it, dump, and the first argument of dump is the file name, is the function name, and that is pan1 in double quotes, and then file is equal to pan1.txt. So we have given the extension .txt so that it can be saved as text file. And to call it, we have to use source, and then you have to keep the file name pan1.txt. So actually sourcing means it is defining. pan1.txt. So that means our function is, suppose somebody writes this function to you and it sends a text file. So you can dump this in the working folder and you can source it, you can call it. So this is all about pan1. Now I have tried to explain the sum of squares, actually sum of squares. This is the concept of sum of squares. We know that the intercept model y is equal to mu plus e. Here this is the y intercept and this is error. Note the fact that summation yi minus y bar whole square is equal to, this is a well known result in statistics, summation y square minus ny bar square. And if you keep this to the left and take this to the right, so what you get, see summation y square, take this to the right. So summation yi minus y bar whole square plus ny bar square. So here this or equivalently summation y square is equal to ny bar square plus summation yi minus y bar square. Thus, this is known as total sum of square. This is known as total sum of square. And this one is termed as SS due to regression. And this one is termed as SS due to residual. With degrees of freedom as, actually degrees of freedom is nothing but how many ways we can choose y. There are n ways. So it is n. And how many ways we can choose this y bar, that is only one way. And how many ways we can choose this yi minus y bar, that is n minus 1 ways, because there is restriction with these. Summation yi minus y bar is equal to 0. So these residual sums must be equal to 0. So in that situation, it is because one sum is known, sum is 0. So that's why we have kept it n minus 1. So this is the interpretation of sum of squares due to degrees of freedom. These are known as degrees of freedom. Now the function Lm I am going to introduce. The function is meant for fitting ordinary least square regression model, namely yi is equal to beta naught plus beta 1 into xi1 plus beta 2 into xi2 dot plus beta p xip plus error for I is equal to 1 to n. The function Lm has two main arguments, formula and data. The formula argument specifies the fitted model, and the data specifies the data frame from which data is taken. It returns almost all the important things which are desired in the data analysis. Suppose actually if we want to take some help about Lm, so what we have to do? Here we have to type the function help about Lm. See, it is in the package, this is the fitting linear models, it is in the package stats, fitting linear models description, Lm is used to fit linear regression model. Usage, Lm formula argument first, then data, then subset, then weights because it works on weighted least square. Na dot action means actually when there are NAs, when there are missing observations, what should be, and then method is equal to QR decomposition, model is equal to true, and C contrast, null offset. So actually formula, subset, weights, Na dot action. Well, so actually these are the arguments of the function Lm. So before coming on these things, I would like to explain what is the concept of example trees. See, example trees, the data frame trees which is available in the package data sets based on in base R is a data frame consisting of volume, columns, volume, girth and height of black cherry trees. To fit this model, to fit this data, an intercept model. Intercept model means there is no covariate. So, yi is equal to beta naught plus ei, and that is the most simplest model, but it is not realistic. Or volume is equal to beta naught plus ei, beta naught plus ei, or volume is equal to mu plus ei. The model is known as intercept model. We use the function Lm to fit this model. See, m naught is equal to Lm. Then how we are writing this formula? Volume we are writing here volume till model as coefficient of beta naught. Coefficient of beta naught is 1 and there is no mention of error, and data is equal to trees. So, we print and we get the result. Then we get summary, print and summary, these are the two. Print gives shorter output, this is the shorter output of the result, this is the estimate of the intercept, and here summary means it gives detailed output of the, see, like here it prints residuals, formula residual, then coefficients, then estimate standard error, t value and p value, and then residual standard error 16.44 with 30 degrees of freedom. So, this way we can fit a model and we can use. See, just I am going to explain these things. So, actually it is, we are fitting this model. So, we have made a chunk Lm tree and m naught is the fitted object Lm volume tilt 1, data is equal to trees. To fit, print the summary of results. So, if we run this control plus enter, we have fitted the model and information is saved against m naught. Now, print gives a smaller output, and if we need detailed output, we have to use the summary. So, summary gives many things.